Here's a problem in which we can practice the concept of independent events. With independent events, I hope you remember that if two events are independent or multiple events are independent, the probability of event A and B occurring, the intersection of the two, is simply probability of A times the probability of B. For example, 4 seeds are planted, each having 80% chance of germinating. These are independent events. The germination of one potted plant does not affect the germination of another potted plant. Find the probability that all 4 seeds germinate. If we consider each of the pots lettered A, B, C, and D, we're finding the probability of A intersect B intersect C intersect D, which will simply be, because they're independent events, we can multiply their probabilities. 0.80 times 0.80 times 0.80 times 0.80, which gives us a probability of 0.4096, or if we're doing 3 significant figures, 410, just about. Okay, so it's about a 41% chance. What's the probability of at least one seed germinating? This is a key concept, at least one. Well, we know total probability is 1. And we're going to subtract, if we want at least one seed germinating, all we have to do is discard the situation where no seeds germinate. Well, when do no seeds germinate? Well, if this is the event A, if event A is the 80% chance of one seed germinating, then the complement of A is the probability that A does not germinate. So this is going to be 0.2 times 0.2 times 0.2 times 0.2. This is probability of the complement of A. This is probability of the complement of B. This is probability of the complement of C. And this is the probability of the complement of D. So we've taken 100%, or 1 total, that's all probabilities together, minus the only situation we have to get rid of or discard is the situation in which all 4 seeds do not germinate. What's the probability of all 4 not germinating? 0.2 times 0.2 times 0.2 times 0.2s, which are the complements of 0.8 times 0.8 times 0.8, 0.8 times 0.8, which will give us 0.9984, or nearly 100% if we're doing it 3 sig figs, 0.998. So we have a very high probability of at least one seed germinating, which would make sense. Let's do some practice with Bayes' theorem of total probability. A box contains 3 black cubes and 7 white cubes. I always think it's helpful to draw it out. 1, 2, 3 black cubes and 7 white cubes. A cube is drawn from the box. Its color is noted, and a cube of the other color is added to the box. If I pick black, I have to add white. If I pick white, I have to add black. I'm always going to have 10 cubes in the box. A second cube is then drawn. What is the probability that the second cube is black? Well, with our first branch in the tree, we can either go black or white. And in our second branch in the tree, we can either go black or white, or black or white. With our first draw, we see that it's 0.3, or 30% are black, and 0.7 are white. If I choose a black, I have to add a white. That gives me 8 white and 2 black. So black would be 0.2 and white would be 0.8. If I choose a white, I have to add a black. That would give me 4 blacks and 6 whites. So this would be 0.4 and 0.6. Well, Bayes' theorem of total probability says if you want to know the probability of getting a black on the second draw, that's going to be this times this plus this times this. It will be 0.3 times 0.2, which is 0.06, plus 0.7 times 0.4, which is 0.28, which will give us a total of 0.34, or we have a 34% chance, or a probability of 0.34. Well, this is black times, this is black times black given black, plus white times black given white. That's what Bayes' theorem of total probability says.